Okay, let's get started. So, welcome everyone. Okay, can you hear me in the back? It's okay. Not so much. Then let me try to increase a bit. How about now? So that's maybe too much. Let's see if there's some echo. Okay, so yeah, it's a bit too loud, right? It's okay. Yeah. Okay, we had a lot of unsupervised learning in the last 2-3 weeks. You saw clustering. You saw the general concept of unsupervised learning, which is quite fascinating because maybe that's the most interesting area of machine learning at the moment, where can we learn if we don't have so many labels available? I mean, if you have to annotate 100,000 images by a human, that's very, very expensive and very tedious. And for the fact what you get from it, you get something which is very narrow in terms of intelligence or being smart, because you can only do this one thing. You can only say if your image has a cat or a dog, but if you give it a zebra, it's completely lost. Whereas if we could do some unsupervised learning, finding a pattern which we haven't predefined, then that's fascinating for like two reasons. So one is now we can just run it on all the data in the world, so we have as much data as you want. And the second thing of it is that it's not task specific, right? It's not because we didn't specify a task. It's not only about cats and dogs. So it's something. That's why unsupervised learning is very nice if it can be done, because you can then use it for any task, right? If you understand something about the data, then it's much less task specific. So it can be reused for many things, and maybe later. On top of this, you might do several different machine learning tasks, which can also be supervised, but having unsupervised method is quite nice. This also relates to like representation learnings, which is basically what it is. So if I have data, the pixels are not the smartest representation, but can I learn a representation which really reflects what the data is? So these would be good features which try to understand your data points, whether it's images or text or audio or whatnot. So that's why unsupervised learning is quite interesting. And yeah, clustering is just a very simplest example of it. We saw mixture models, which is a more advanced version of that, which is again to group data, to maybe assign it into groups or soft assignments. And today we go a bit further. We look at matrix factorizations, which are used for many things, and they are used for both supervised and unsupervised learning. So, and yeah, we will actually see that also what you saw, k-means, is also an example of matrix factorizations. Yeah, that's the plan for today. Also about the project, so I hope you guys are on track. So if you have any questions, so please use the Moodle forum. It's important to exchange, right? So this, especially if you do an interdisciplinary project, it's difficult to get the input from both sides. So write in the forum, we will answer. And also in 2 weeks we will offer a Q&A session where you can come. We will offer 3 sessions during the whole week. You can come with your mentor from another field if you want to get input, discuss your approach. And that's also for no matter which project you do, you're welcome. And of course also the regular exercise classes, yeah. Yeah, the new lab is also online. This week you can play with Python again, try to implement a matrix factorization. Any questions on the schedule, logistics, or everything good so far? So, okay. Let's go into business, and we will look at the Netflix problem, how it's called, and that's a big This was like a competition, has been a few years ago, where Netflix actually published a data set with a ton of data of users and movies. So here we have, on the rows of this matrix, you have the movies. So that's what we call the index D. Goes from 1 to D if you want. And then, is it visible or too much light? Okay. And then in the columns we have the same thing, but here it's not movies, but it's the users. So what this thing is for every user n, and the movie D, so this is called the user, which corresponds to the column. Yeah, we got this data, how many stars the user gave to the movie, if he liked it or not. So 5 stars is the best, 1 star is the worst. And the data set that they published actually was very nice. It had 20,000 movies. That's D. That's not so much, but that's still a nice number. But also very interestingly, it had a lot of users, namely 500,000 users who gave some ratings. So that's the columns. And so you don't have all the ratings, of course. So like 99.9% of this matrix is unobserved. That's the gray area. So there might be a few more 9s here, I'm not sure. So I know how many entries they actually had, and that's 100 million. So that's the entries where we have stars from 1 to 5, and all the other ones are the gray ones where we don't have. So this matrix is actually quite big, so it would be impossible for you to store on a computer if you just store it as a matrix, a full matrix. So that's quite important to keep in mind. But if you only keep the ratings, so how do you keep them? You just keep them as a list key value, right? So the key is movie 2 and user 3, 2, 3. So that's the movie user, and then you put the value, how many stars. So user 2, messing this up, movie 2, user 3. How many stars? Yeah, we got 4 stars. So I put all this in a very big list, and this way it's very easy to store this matrix. It's just a 100 million vector times 3. So 2 keys and 1 value. So that's the rating. Okay, and the task here was to, given this data, predict some of the missing ratings, some of the entries which we don't have, but maybe Netflix still has some additional ones, and on that additional ones, that's your test set, there they evaluate you how accurate you are predicting. So the task is given one movie, one user, where I don't know the answer, for example, this one and this one. So yeah, what's this missing entry here? That's what we're trying to do, and that's what a recommender system is. So we need to recommend movies to people. So because if you actually do this for an entire row here, so this user n, you just figure out all the gray entries here in that column of that user. If you predict all these gray entries, then you have a good list of movies, well, all the movies, and then you just recommend the top ones, the one you give the highest prediction of stars, those you will recommend to your customer. Okay, so I hope the task is clear. We're given the white entries. We want to predict all the gray entries, and the prediction should be numbers from from 1 to 5. So it's kind of a regression task. But it's, well, yeah, actually it's called ordinal regression because people want integer numbers, but it doesn't matter. We don't care about that. We will just predict numbers. We'll predict, here we will predict, yeah, 2.5 stars. That doesn't exist, but anyway, that's my prediction. Fine. So, and in the end, I will just say this is my best guess, and I will rank them by their scores. Yeah. Yeah, this data set is very interesting, and it also is not available anymore. So later, people realized that there are privacy issues even in that data set. So they just gave IDs to users, and well, the movies are public, but yeah. But even here, so if you just know this user has watched this and this movie, then people were able to match that with some other publicly available data. So they were able to identify some users, which then was a big problem. So now we cannot play this with this nice data set anymore. So, but if you want it for research purpose, I still have a copy. So, so that's this. And so this was a big competition. Actually, this the company gave $1 million, if I remember correctly, to the team which could predict this with the highest accuracy. So a lot of people started. So this was like the first big like kind of machine learning competition. Everybody got very motivated, and it was nice because at that time it was not so clear how to approach this. What are good arguments for this, right? This is not a simple cats and dog classification problem, but it's a bit more unclear what would be the best thing to do here. Also, the methods, they don't give you any information about the user or the movie. They only give a movie ID and the user ID, right? We don't know what kind of movie that is and what kind of user that is. The only information you have is how many stars they give. And surprisingly, that works. It actually works even better than if you would use information of the users as well and of the movies. So, okay, that's the task. Any questions on this? So yeah, just the notation is movies are columns indexed by rows. Users are n, which are columns of our matrix. So X is this matrix now, but keep in mind that X is kind of an incomplete matrix. It doesn't mean that it's 0 here, right? It means really we don't have an entry there. It's unobserved. So, but that's our input, and our task is to predict the missing ratings. And let's do this. So, okay. So the easiest approach to do this turns out is to do a matrix factorization, and that you actually have seen already in k-means. So k-means was a bit similar. We had a data set, and it turns out we were able to write our data as product of two matrices, and that's the same thing as we're going to do here. But what is a bit different now is, first of all, we don't care about assignments or so, or that set needs to be an assignment matrix. And also the main difference maybe is that the data X, it's not a full matrix. Here we only have some of the entries. So we cannot talk about the majority of the entries of X. We still need to do something. So what do we do? So what it means is that we will try to approximate X, but only the observed entries. And so we'll do this as we are used to by actually defining a loss function, a cost function. So yeah, let's first clarify again the dimensions, what we're trying to do. So our parameters are W and Z, which are both matrices. And let me write them because it's very important what shape they have. So we will, so Z is here, is actually a flat matrix, and W is a thin matrix. So we have to make sure that dimensions actually match. So we have to decide on a dimension here, which we call K. Remember that from K-means, maybe it's a bit similar. So, well, yeah, if you want to multiply two matrices, then these dimensions must match. So we need to choose a K. And the point here is that we choose quite a small K, because the number of rows here is gigantic. So we have D rows, and we have n columns. So that's very, very big. So the point I want to make here is you could never even store the X matrix if it was full n by D. That's impossible because I gave you the dimensions. But these two matrices here, they're quite manageable. They're n by D, they are D by K and n by K. So that's much smaller, because K in these applications will be a very small number, like 10 or maybe 50. So let's clarify this again. So actually, W is called the movie matrix. And then this other thing, Z, is called the user matrix, right? And it has n columns. Why is that? Because, yeah, Z has a row for every user. Why row? Because, well, it's transposed. And W has a row for every movie. That's what it is. D by K. And Z is the same thing, but with n. So n by K. Okay, and these are the variables. This is what we need to find. And how the prediction works is just by the matrix product. So I want to know what's the ij's entry or the dn's entry. Now small d, small n. And I'm trying to do this such that my x. So here is x, which I'm trying to predict for a particular d and n. And how do I predict it? So this is how many stars we have. I'm predicting it, well, by this entry here. So this is my model, if you want. And it's very simple, right? It's just multiplying this green row of W with the corresponding column of Z transpose. So you take row WD and you multiply it with the column n of Z transpose, which is actually the nth row of Z. So the dots I wrote is just that the column is anything you want, but the row is n or d respectively. So that's how we compute the product of two matrices. Not so surprising, but this is our model, and it's still very important to understand why this model is defined in this way, right? Because that's all we do. So it's nothing else to do, and this actually works. So we can approximate x in a meaningful way, which is the product of these two matrices. Now let's just find the W and Z. and that's what we have to do. And how does this go together with the loss function? What do we say? What is a good fit of our model? Which one fits the training data well? Yeah, let's just use least squares error. So let's use the squared error, which is what's written here. So that's, you sum up all the entries, what they should be to what they are. You square that, and you sum up over all the observed entries. So there's an important notation here. So omega, that's a set of pairs of indices. So that's written on the bottom. So this is collecting the white entries, the ones which are available, which are observed in the data. So the interesting thing about this objective is that it only depends on the observed entries. So you could do this on the whole matrix. That's basically what we did in k-means. If you remember there, it's when you do this on all the entries, it's actually going to be the Frobenius norm, if you remember. Just summing up the squares of all the entries, that's the Frobenius norm of a difference of two matrices. But here we only do this on a subset of the entries, the one which you observe. So this omega here is very, very crucial. So it's not over all, but over this omega. And then, yeah, sometimes you normalize by the number of entries you have, so then it's kind of average, or here it's just the sum, it doesn't matter. So this is the crucial thing. This is our cost function or loss function, so for training. Okay, and why is this called a matrix factorization? Well, yeah, because you form a product of two matrices and then you put it into a loss function. So more generally, what are matrix factorizations? Any problem which is of the form minimizing some cost. So maybe the cost is okay. Let's write it out. If I minimize the cost, which depends on the two matrices, and if that cost turns out to have the form that it only depends on the product of these two guys, so it's actually a function which takes one matrix. So f takes this one matrix, which is the product. So if your problem is of this form, then we say that's a matrix factorization as an optimization problem. And the example you've seen, that's one of this form, right? Because here, what is f? Well, f is just forming the sum over all differences of the observed entries. That's your f. So, and you minimize over w and z. Okay, these are matrix factorizations in general, and the example we have here is the one with the least squares cost, which is maybe the most important one. It's also the one which is easiest to optimize. But if you want to play around with this, you will see that actually it can be even nicer to make it robust, to make it the absolute values instead, like we had with, if you remember, mean absolute error. That you could also do here, replace the yellow part with absolute values, and then you would have an even more robust method. It's a bit harder to optimize then, but you actually have all the tools. You can also optimize this if you want, if you remember the same thing from the regression case. Why am I saying this? Because the whole matrix factorization is also one of the options in project 2. If you want, actually what you have there is a similar data set, and you can try out different variants, see if you can improve the prediction accuracy in such a setting. Okay, any questions about this part? Does this make sense to use this kind of loss function? So. Okay, what we should also keep in mind is how expensive it is to compute. as we said, you could never even store a full matrix. So is this actually fine? And yes, it is, because the model, I mean, you're never going to form the full W times Z, right? That's not what we do. But when you compute this sum, then you just look at a particular dn, so that's one entry, and for that dn you pick the corresponding rows and columns and multiply them. So that's what you have here, right? How much does that cost for a fixed dn entry? Any ideas? If I tell you, I want to have the prediction of my model at position dn. Any? The candidates are d, n, k, pi, I, and 0. Or my math teacher always said that in these questions it's either 1, -1, or pi, the answer. So no, to get one entry, of course, it costs k, right? Because k is the number of columns in our W and Z matrices. So again, k is very small. K is 10, whereas n and d are millions or billions. So that's fine. I can compute this sum very efficiently. And also when you have trained the model itself is quite small. W is okay, Z is okay, they're not big. The product will be impossible. So you can give W and Z to the customer, and when they use the model, it's very easy. They will only pay K per prediction. So pick a user, pick a movie, form the inner product of the two vectors. That is your prediction, you're done. So it's very efficient at prediction time. And if you want to compute this whole loss function, then that's also manageable then. But then you have to go over all the observed entries, compute the prediction, and sum them up. So yeah, that's what I was talking about here. It's just to say that keep this in mind. K is much, much smaller than D and N. So okay. That's all about the setup, and now we have to ask, how do you actually train such a model? How can we find the best W and Z? The nice thing is we can use exactly the same methods that you already know. So we will use optimization, and we will just basically do gradient descent here. So we'll get to that in a minute. So it's just, yeah, so you minimize the cost, and you just have two variables. It doesn't matter. So W has a huge number of entries, Z has a huge number of entries. You can concatenate them all, and now you say you have a huge number of parameters. So there's just two kinds of them. So, yeah.
Can you repeat what the omega is?
Yeah, what is omega? So omega is given. That's just marking which entries are observed. So the ones in omega, we have a star from 1 to 5. And the ones not in omega, we don't know, so we are asked to predict them. So there were the omega is the white entries, and not omega is the gray entries. So not omega is 99.9%. So yeah. Any other comments? Okay, so let's try. Can we optimize this? And this, if you want to optimize this function, some question which comes up is, so is it actually convex? Can we find a minimum here? And is the solution unique? So that's another. So that's what we mean by identifiable in the end. So you can help me a bit. Let's do maybe the easier part first. So identifiable. So here's my loss function. Remember this one. Is So let's say I give you the solution. Now here is, well, yeah, W, Z, which are the optimal ones. Is this unique? What would you say? Is this the only solution? Who thinks this is not unique? Who thinks the solution is unique? Oh, wow. So, no, we don't have a regularization at the moment. We only have the cost function as given here. So I hear it's not necessarily unique. Yes, so it's not unique. Why? Because it depends only on the product of the two variables, right? So, okay, I give you W and Z, but you're correct. Given that, you could just shrink one of them by 10 and multiply the other by 10, right? So then their product is unchanged. But, so yeah, now I have a different pair of W and Z. So this is to talk about identifiability, so it's not identifiable. And why? So we use the notation similarly with W star, Z star, and yeah, if you have that, so form a new solution. Whatever, how should I call this? Beta times W star, and then the other colleague you divide by the same factor. Yeah, so if this was a solution, then this is also a solution. Is also optimal. Okay. Then, so that's okay, right? It's not super important that the solution is unique, because, well, we mostly care that we get good predictions. That's the more important task for us. But well, yeah, we discussed this a bit, that some functions actually do have unique solutions. So if it's the case, nice. But if it's not the case, we can still do some work, and but it's important to understand that there is this symmetry here. Then, okay, the second one we want to know if this function is convex or not with respect to the parameters. And the parameters, there is a huge number of parameters. They're in two groups, right? So you can write them in one big vectors. First, all the entities of W, then all the entities of Z. So we have a lot of parameters. How many actually? Anybody? So. So it's, yeah, the dimensions of the two matrices added up. That's n times k plus d times k. That's the number of parameters we have when we try to solve this optimization problem here, right? Yes, so question, is this a convex function in these parameters? So who would say it's not convex? So, and who would think that it's convex in these parameters? Yes, it's very natural to think that it's convex because it's a very simple function, right? It's just the square of this simple product of two matrices. So, but unfortunately, we are wrong with this intuition. So it's actually not a convex function in these parameters. So why not? Any example you could think of, or it's not so easy? That's a difficult question actually. Or do you see how would you check if it's convex? Or can you think of an example for this? What would you try? try the simplest case when W and Z are quite small, maybe. So. So the simplest example I can think of is when W and Z are only a number each. So then we're just multiplying two numbers. So these are 1-by-1 matrices. That's the easiest example to think of, maybe. So let's give that a try. So yeah, I'll just look, we will look at 1-by-1 matrices. So when the loss W and Z is just I don't need to write the transpose, right? Because there's no point to transpose a number. So that's my function I want to look at, and so this is a function in taking two-dimensional input and outputting a number. Well, the cost is always a number. So this is a very valid loss function, an important loss function to consider. Well, it's just a very simple example. But can any one of you can see why this one is not convex? How would you try to prove it? So we have seen many definitions of convexity. So maybe there are different ways of proving it. So. Yeah, you could compute a Hessian matrix of the second derivatives, but that's quite complicated. It's quite hard. Well, no, not so hard in this case, but I always find it complicated, so try to avoid it. But yeah, so the derivatives would be quite simple for this. This we will actually do in a minute, and then the Hessian, when you differentiate again, then you would see that the Hessian. Well, yeah, you could actually do this. If you want to do this, you will see that second derivative of this stuff is actually this matrix here, which has ones on the off diagonals. So you can convince yourself that this is the case. And this, so why is it? Because the first derivative with respect to W, what's that? That's actually Z, and then what's the derivative with respect to Z? That's actually W, and then you do it again, and then you get that the second derivative is this matrix. Now this has ones on the off diagonals, and some people know that this is not positive semi-definite, so therefore it's not a convex problem. This is one way of doing it, if you're familiar with matrix calculus, which you actually should be. So. There is another similarly simple way of proving it. What else could we do? So any other definition of convexity you have seen, then we could try to take this definition and see if it holds. Well, the easiest definition of convexity is the line segment thing, right? For any 2 points on the line segment, the line should be above the graph of the function. So that's the other thing you can do. And let's do this. This is very simple here. Let's try to understand our function going from R2 to R, So there are two variables here, w on the x-axis and z on the vertical axis. And the function is we have is a bit interesting because it's positive here, it's negative here, positive here, and negative here. If I got this correct, yes. And this already looks a bit fishy for a convex function. It's a, or what could we do now when we have this landscape? So if it were convex, then any line segment would be, would have the property. Now, here, can you find a line which violates this condition? Yeah.
I'm sorry, but for me, the last function should be the w times z to the square, right? Because that's how it's actually.
Well, yes, you're saying the loss should be squared. For this example, yes, you're right. But I'm talking about any loss function here, and so this here is just one choice of loss function, right? But we said here that we can consider loss functions anything you like, as long as it only depends on the product of f, product of w. So what have I done here? I have used the f being the identity function. So yeah, that's a bit a stupid cost function. I agree with you. Doesn't make so much sense. Nobody would do this in a machine learning application. But if it doesn't work even for the simplest f being the identity, then it's definitely messed up or difficult to do, right? So we're asking, is it convex, right? So the answer, what we're going to prove now is, no, it's not convex even in the example when f is the identity. So now we just make the f more complicated when we do the f actually using these least squares, the difference to a prediction. Then yes, you could try to prove that again, but if it's not even convex in that even simpler example, then there is not much hope. So I will only show it for the simple example. I will not show it for this particular square cost function. But you could try to do that as well. So thanks for your comment. It's very useful. So I consider f is the identity as an example, because I only need to find a counter example, right? I can choose where I want to find a counter or where I want to find the contradiction. Okay, so if f is the identity, then this is equal to w times z. So yeah, I should have written that actually. So if that's the case, then the landscape looks like it was drawn. And now it's very easy to find a pair of points where the line segment is not above the function. So it will violate this convexity assumption. So actually between here and here, if I choose 2 points, here it's probably fine because it's going up, right? The function is actually 0 in the middle. So this looks like convex because it should be, the line should be above the graph of the function. However, if I choose 2 points in those regions, then the values they are both negative, and the value in the middle is 0. So when I look at this line from the side, then here is how that would look like. I go from point 1 to point 2, and so yeah, here in the middle it would actually be the value 0. So this is clearly not a convex function. This is exactly what contradicts the property of being convex, because convex would mean the purple line would need to be above the graph, and it's not. So I found a counterexample. It's not a convex function. Yeah, that's a bit abstract as written now, but what the intuition is that these products of two matrices, they look a bit like saddle functions. So when you go to the upright, it goes to plus infinity. When you go to the left top, it goes to minus infinity. And then on the lower left, it's okay again, goes to plus infinity. And then bottom right, it's again going to negative infinity. So this is a saddle function, going down on two sides and going up on the other two sides. And that's an example of a non-convex function. Just one last question before we go into the break. So what if I only ask you, let's fix one of the two matrices. Let's fix let's fix W. Now, is this function convex in Z? What do you think? So, who would say it's convex in Z when W is fixed? Yes. Who would think it's not? So, nobody? Yes, that's a good majority vote, even if you have too small vote participation, but we take whatever we get. So and you guys are correct. So yeah, if you fix one of the two variables, then in the other it's convex. Why? Because, well, if you fix W, then this is basically the identity function. It just takes Z and multiplies with a constant. So of course, that's not doing anything evil. That's a identity function, which is convex. Yeah?
So depending on the loss function, you will not always have convex loss.
Yeah, it depends on the loss function f if you have this property. But what I showed you that is, even for the most simple f identity, even there, it's not convex. So there's not much hope that for even more complex loss functions f, it would be convex. And you could actually show it for the square loss as well, but we're not going to do this. Anyway, we will not want to spend too much time actually, because we will use the same algorithms anyway, no matter if this function is convex or not. So the nice thing about this problem is it's kind of a moderately non-convex problem. We still use gradient descent. It works perfectly. It's actually very surprising how well it works. And this function does, in practice, not have any local minima, which are nasty. So, and that's actually a very active field of research, that there is no much understanding yet to prove if this function has actually local minima or not. This is very unclear. It's quite surprising, because you could think this is such a simple function. Well, the example I gave you in blue, that's understood, of course. But now if you take the real loss function, which you guys rightfully wanted to do, the square thing, and if you do it over a partially observed set of entries, then this is very difficult to understand if this might have local minima or not. But we don't mind so much. We will just run gradient descent, and it works in practice. And that's what we're going to do after the break.